This is section 6.2, systems of equations and inequalities in two variables. Now basically what are linear inequalities when two variables? The best way to think of them is think of their solution set, which the graph of a linear inequality is basically a half plane. And we know linear inequality is less than, greater than, less than or equal to, or greater than or equal to. And basically the half plane has a boundary, which is a line, and the boundary line is included when we're talking about less than or equal to or greater than or equal to. So in other words, the equal part tells us we include the boundary. And if I simply have less than or greater than, I simply don't include the boundary. Now the question is, once I split the plane in half with a line, how do we know which part to shade in? And for this, we simply pick a test point, and the only requirement we make is that the test point cannot fall on that boundary line. We plug the test point into the inequality, and if it is a true statement, then we shade the side the test point's on, and if it's a false statement, we shade the side that it's not on. Let's look at an example. Graph the solution set to the inequality 2x plus y is less than 8. We're going to first start by graphing the equality, graph the boundary line. I'm going to graph 2x plus y equals 8, so I get y is negative 2x plus 8. This is now in slope-intercept form. Go up 8 to my y-intercept, down 2 and over 1 is my second point. I'm going to use a dashed line for my boundary because this was strictly less than. So here's my boundary. Now I got to pick a test point. In all honesty, the easiest test point to always pick is 0, 0, as long as it's not on the boundary. In this case, 0, 0 is not on the boundary. So I'm going to now take my test point 0, 0 and plug it into the equation 2x plus y is less than 8. So 2 times 0 plus 0 is less than 8. So is 0 less than 8? Yes, that's a true statement. So now I'm going to shade the side of the plane that the test point is on, and notice I shaded down and to the left of the line. Now I can also do nonlinear inequalities. I can graph the solution set to the inequality x squared plus y is greater or equal to negative 2. First I want to sketch the boundary. I have x squared plus y equals negative 2. So y equals negative x squared minus 2. This is a parabola facing downward, shifted down 2 units. I'm going to use a solid line in this case because this was greater than or equal to. And again, I'm going to pick a test point because the test point 0, 0 is not on the graph. So is 0 plus 0 greater than or equal to negative 2? This is a true statement. So this parabola is facing downward, so I'm going to shade the top part away from this parabola. Let's look at systems of linear and nonlinear inequalities. Just like graphing a single line or other function, we will use the same procedures and simply graph multiple lines or multiple functions. Now we can use test points again. We can actually use the same test point as long as the test point doesn't fall on a boundary. And the final solution is actually going to be the intersection of the individual solutions for each test point. So let's look at an example. Graph the solution set to the inequality 2x plus y is less than 8 and x minus y is greater than 4. Now in this first one, we already solved this first one up here. This x plus y is less than 8. That was this graph in the upper left. So what I'm going to do is graph the other one, the equality to the second one first. X minus y equals 4. So y equals x minus 4. So I have a slope, y-intercept of negative 4 and a slope of up 1 over 1. And again, I can do a test point of 0, 0. So 0 minus 0 is greater than 4. That's false. So I'm going to shade on the opposite side of the test point. So now I have two separate graphs, okay? My actual solution is the intersection of these solutions. So I graph the two lines here, and I only graph the portion of the graph which is true for both of them. And that's down here in this bottom left quadrant here. This is true for this right graph, and it's true for the left graph. If we wanted to, we could actually graph them both, do our shaded lines here, and then where they overlap is where I would shade in. This leads us to our next topic of conversation, which is actually linear programming. And linear programming is a procedure used to optimize quantities such as cost and profit. A linear program consists of a linear objective function and a system of linear inequalities called constraints. We will talk about both the objective function and the constraints. And the solution set of linear inequalities is called the set of feasible solutions. This is how we're going to do the linear program. We're going to read the problem carefully and make a table for the information. We're going to use the table to write the constraints. We're going to sketch a graph of the feasible solutions. The shaded area will be the feasible solutions. We're going to identify all the vertices. The vertices are basically the place where the lines intersect. And then we're going to evaluate the objective function at each vertex. The vertices are where we're going to get our maximum or minimum from. Let's look at an example. This is a very simple one. A company manufactures two projects, large basketballs and small basketballs. A large basketball yields a profit of $25, and a small basketball yields a profit of $10. Due to demand, the company must produce at least 10, but no more than 60 small basketballs per day. The number of small basketballs cannot exceed the number of large basketballs. The number of large basketballs cannot exceed 75. How many of each type should the company produce or manufacture to obtain the maximum profit? We're going to start by letting X be the number of large basketballs and Y be the number of small basketballs. Our profit is 25X plus 10Y. 25 being the profit for the number of large basketballs, 10 being the profit for the number of small basketballs. We're not going to do our constraints. Due to the demand, the company must produce at least 10, but no more than 60 small basketballs per day. So therefore, Y has to be greater than or equal to 10, and Y has to be less than or equal to 60. Here's my first equation. Y is greater than or equal to 10. I got to shade up. Y is less than or equal to 60. I got to shade down. So every one of my solutions has to be between 10 and 60 for the Y. The number of small basketballs cannot exceed the number of large basketballs, so Y is less than X. So here's my boundary line. Y is less than X. I probably should have sat there and made this a dashed line. I apologize for not doing that. We plug in and we shade downward. The number of small basketballs cannot exceed 75. Well, here's the number of small basketballs. X is less than or equal to 75. So now I have all my constraints in place, and these are my feasible solutions fall in this shaded area. Now we need to make our table. We need to identify our vertices. These are where the lines intersect at. They intersect here at 60, 60, because this is the line Y equals X, and this is the line Y equals 60. This is the line Y equals 10, and this is the line Y equals X, so this is 10, 10. This is the line X is 75, so I have 75, 60, and 75, 10. So I now have all my vertices, and we make our table. The vertices are 10, 10, 60, 60, 75, 60, and 75, 10. Here was the profit function, 25x plus 10y. I'm going to take each vertex and plug it into the profit function. My first vertex was 10, 10. 25 times 10 plus 10 times 10 is 350. Therefore, if I made 10 large basketballs and 10 small basketballs, I'd have a profit of $350. If I made 60 large basketballs and 60 small basketballs, it'd be 25 times 60 plus 10 times 60 is 2100. The vertex 7560 gives us 25 times 75 plus 10 times 60, which is 2475. And finally, the last vertex 7510 gives us 1975. Therefore, our most profit is made when we produce 75 large and 60 small. The least profit is made when I produce 10 of each.